Uh, Hello, am I audible? Can anyone uh, just respond? Hello? Yeah, okay. Uh, so let me just start the recording. So you all can see my screen, right? Yeah, cool. Okay, let's get started with this live session. Yeah, cool. All right. So this is Sai Dinesh, your TA for this course, and I'm a PMR TS. I'll be taking live sessions every week, covering the topics that are being taught in that week, right? And I am a PhD scholar from IIT Madras, and I am the TA for digital signal processing here. So today we will be covering topics from week 1 and week 2, covering from the basics of signals and systems, like how discrete time, continuous time, and all that, and then we move to periodicity and all that stuff. Let me just check if the recording is proper. Can anyone just say speak something, please?
Yes, sir.
Yeah, okay, cool. Yeah, thank you so much. Okay, let's get started. So this is digital signal processing week 1 and 2. So first I'll be covering week 1 for 1 hour and then week 2 for 1 hour. So very briefly I'll go to the basics of signal systems. So what we see in real life are usually what continuous time signals that we have, but then we can't 1 second, I'll just turn off my video. Yeah, let's just continue. So these are the real time signals that we usually see, but then we what we do in real world is that we process these signals. So for the processing we use computers, and we can't do everything in real time. So what we do is discretize them, okay, and then we bring it into digital domain. So that is where the digital signal processing actually comes into place. So one example is sampling, that you all know. So like this is a continuous time signal, and then we sample this signal at a particular rate t 2t. So now what we are left with is a discrete signal. Now there is a difference here. So there, this actually is still a continuous time signal only. I have not yet gone to the discrete signal. So there's discretization and then digitalization are different here. So here it is discrete. We are taking samples at the same time. So it is t, 2t and 3t, and these values are still zeros here. But then still this is in continuous time. But then what we do is, and then we bring it to digital domain, and then in digital domain what we have is these same samples. The sample at t equals to the sample at 1, and sample at 2t equals to sample at 2. So now it is in actually a digital domain. So this discretization and digital are different. So simply sampling a real-time signal does not give you a digital signal, right? So this is called sampling and then conversion to signal. Even if you later in this course you will see that the Fourier transforms that you encounter in the later part of this course, the Fourier transform of a discrete signal and the Fourier transform of a digital signal are quite different, right? So that is one thing to be noted, and then we'll go to that in the next part here. And then one more thing to be noted is, just very briefly, these values in between do not exist, right? Yeah. So this is like the basics of what digital, what this is a digital system. So these are digital systems, and then next what we have is from digital. So this signals will go into digital systems, and then we work with digital signals, and then we get an output here. So these digital signals also work in the digital domain, right? If at all you have any doubt, you can just interrupt me in between, right? Okay. So yeah, so here we have n only, which is for, and then these n are only integer numbers belong to z. Okay, so now these are the digital signals. Now yeah, like as I said earlier, x of n for n belonging to integer, and then sorry, x of 1.5 does not exist, right? Yeah, so now briefly we can characterize the signals into two types, which one is periodic and then one is non-periodic, right? So in the I mean, as you'll see again in the later part of the course, every signal what we do with Fourier transform is we split it up into a different many number of signals, summation of many number of signals of different periodic signals. So innate summation of many periodic signals is there. Okay, so periodic and non-periodic, and then many other characterizations are there, like even, odd, causal, anti-causal. There, I'll just go through them in a bit. Okay, yeah. So that is one thing, and then so what I'll be talking about here is, first one will be periodicity, periodic, non-periodic, and then next I'll talk about energy and energy signals and power signals, right? Yeah, so these are some things that I'll be talking about next. Okay, yeah. So yeah, so first just let's just talk about energy and power signals. Okay, so energy and power signals. So if an L2 norm of x, which is the summation of the square of each point of x at t, is infinity. Now here, if you note, it is continuous. So if at all, if I am writing it as xt, it is continuous, and if I am writing it as xn, it is discrete. So this is the notation that I'll be using, right? So if this energy is like the sum of the square terms of integration over the all terms. If this is finite, then it is an energy signal. So basically all I'm saying is that if the energy of a signal is finite, it is called an energy signal, right? For an example would be an example would be xt is equal to e power minus t for t greater than or equal to 0. So this is an energy signal, right? And then e power t is not an energy signal. So this is monotonically decreasing, right? So this is the energy is finite. But if you have a monotonically increasing signal like e power t, then it is not an energy signal, right? And then next we move on to power signals. So now if limit t tends to infinity, 1 by t average over a particular time period from minus t by 2 to t by 2, and then the same whole square is in less than infinity, then it is called a, now this energy, this is the energy over a finite period of time, which is the time, one particular time. So this energy per time is power, you all know, right? So this is a power signal we have here, right? So if now this is a power signal, I can say one example would be xt is equal to a times cos omega naught t plus theta. So a cos signal, all I'm saying, it is a cos signal. So that can be a power signal, right? Now 1 second. Okay, So I'll go, I can give a few examples of this thing. One would be, sorry, 1 second. Yeah, x of 3. Now for example, if we have a signal like x of n. No, so this what I've been talking until now is completely continuous. The same case goes for the discrete time as well. So if we move this as a summation over x of n whole square over all n, then it is a energy signal in discrete time. Similarly, it goes for a power signal also. Okay, yeah. So if I take a signal like let's say example x of n is equal to 1 by 2 power n into u of n. So u of n is a step signal that I'll be, I mean, I'm sure you all know, but then I'll have to cover it up later. I mean, I'll cover that again later. So so it is like 1 by 2 power n for n greater than or equal to 0, and then 0 for n less than 0. So this is what it means. So here it is a monotonically decreasing signal because 1 by 2 is less than 1. So if we take if we find the summation e infinity is equal to n equal to minus infinity to infinity x of n whole square is equal to 1 by 4 power n summation over all n, which is equal to 4 by 8, I suppose. 4 by 8, yeah, if you do the arithmetic progression here, or sorry, GB. And then if you find the power, so since this is a finite energy signal, and then 1 by t over this power or this energy would be equal to 0 since t is tending to infinity here. Yeah, so what we have is e infinity equal to 4 by 8 and p infinity equal to 0 here. This is the energy signal that we have here, right? So I think, I suppose you guys got an intuition of energy signal and power signal here. Now let's talk about some properties of some signals, or how we deal with signals, right? So let's just go through few of them. So let's say you have a signal x of n, and then and also let me know if you guys want me to explain a particular topic which I don't cover in this session. Maybe I can do it now, or else I can do it in the next class, right? For no, so this is a signal x of n that I have, right? So, and now this is a discrete signal that I have. So two main attributes of a signal is, one is a support set. So this is a set of indices for which x of n is not equal to 0. I mean, like, if x of n has support, like if x of n has support n1 to n2, this means that x of n is 0 for n less than n1 and n greater than n2. So this is what support set means. And then second attribute would be the length of the signal, with the length of the signal. Okay, so length of the signal. So if for a particular support, let's say if x of n has support n1 to n2, then what would be the length be? Length is equal to, sorry, n2 minus n1 plus 1. So this is the length of the signal. And one more notation that I'll be using is, so digital signals here are can be considered as sequences, right? So x of n can be like a sequence of numbers, so minus 1, 1, 2, 4, minus 5, etc. But then how do you define it as a sequence? So how do you know which in this corresponds to this? Then I put an arrow. So this corresponds to n equal to 0. So this n equal to 0. So wherever there's an arrow, one sec, I have to admit someone. Yeah. So wherever there's an arrow, that corresponds to the 0 n equal to 0 part. Now, if x of n belongs to R for all n, then x of n is a real valued signal, and if x of n belongs to complex for all n, then it is a complex valued signal. Correct? Yeah. And then next one. So let's just next go to the I'll first go through some elementary signals that I need to talk about. So some fundamental signals. So since this is a first week, and then most of the topics that I'll be covering here would be from signals and systems basics. So I think many of you might be aware of these things. Just bear with me for a moment, because I mean it's good to always revise these topics before we dwell into the deeper concepts, so that like each and everything, like for example integer value non-integer values of a discrete signal don't exist. So these kind of minute details will actually are important when you actually go into the deeper technicalities of the Fourier transforms or whatever digital signal processing algorithms that you'll be applying for later, right? So fundamental signals are, one would be the impulse signal. So all I'm talking about here right now would be in the discrete case. So what we are concerned about here is a discrete case. So for in the discrete domain, an impulse signal would be delta of n equal to 1 for n equal to 0 and 0 for n not equal to 0. So it's like one here, and then it is zeros everywhere. So this actually impulse signal is actually really important, because we characterize a system based on the impulse response of that system. Like for a given system, we give an impulse signal as its input and see what the output signal is, and then later we will see that all signals can be characterized as a sum of many input impulse signals. So due to, like, if it is a linear system, then in that case we can characterize the system. Basically what I'm saying is we can characterize the system by its impulse response, how the system's response to an impulse signal, what the output is for an impulse response. So this is a very important signal that we'll be seeing throughout the course everywhere. So if we want to like represent this as a sequence, then we write it as 1 and then 0 0 gone. So 1. So this is a impulse signal. And then second one would be unit step signal. For unit step signal, u of n would be 1 for n greater than or equal to 0 and n less than 0. So here the support of the signal is 0 to infinity, right? And the length is also an infinite signal. So this also is a really important signal which we'll be talking about, like when you characterize a system as like causal, or you extract out the positive parts of it. I mean also you'll be seeing this in the Fourier case, like if you want only the positive bandwidth and stuff like that, you'll be seeing these later. So these fundamental signals are really important to know and to understand them properly. And then unit, as you might have guessed already, this is a unit step signal starting from 0 1 2 and then so on, and then zeros for all lesser. Yeah. So third one would be a causal signal. Let me just check, ensure that everything's working. Yeah, Yeah, it's recording. Yeah. So next is a causal and anti-causal signal. So these are a type of, characteristic of a signal, as I must say. I've seen, yeah. So causal, let's talk about causal signal first. So a causal signal is a signal x of n for which uh, all the values of that signal will be 0 for negative indices. So basically x of n equal, an example would be x of n for a of n for n greater than equal to 0 and 0 for n less than 0. If you see only for the positive values, so basically x of n will be 0 for n greater than or equal to 0 and x of n equal to 0. Sorry, this is a wrong statement here. It's my mistake. So causal signal will be x of n equal to 0 for n less than 0. So this is what causal signal means. So this is an example of causal signal here. So A can belong to complex or real domain. So now if mod A is less than 1, then x of n tends to 0 as n tends to infinity, and then if mod A is greater than 1, x mod x of n tends to infinity as n tends to infinity. So this is a type of a causal signal that we have, and if we see, so this is a monotonically decreasing function and this is a monotonically increasing function. So this here is not fully summable, so it means that I'm saying that it is not energy signal, you can say, right? So the support of these signals will be, not generally causal, but support of this type of signals, this signal that we have is 0 to infinity here, right? And then similarly what we have is an anti-causal signal, for which x of n equal to 0 for n greater than 0. So this is an anti-causal signal that we have here. So next, let's just talk about shifting and scaling of signals. So this is a really important operation that we'll be talking about, right? So let's say you have a signal of n of n, and then you apply it to a signal solar system. Is my voice audible properly? Am I loud enough? No one's responding. I hope it is fine then. Okay, so let's say you have a signal x of n and then you send it to a discrete time system and then you get a y output y of n. So let's say this output x of n is x of something like ax plus b, like where a and b are constants, right? So this is a scaled and a shifted version. So let's just talk about shifting first. So shifting is, let's say, x of n and then you pass it to a system, discrete time system, and then you have a x of n minus n naught. So this is known as shifting, and then particularly when n minus n naught, if n naught is greater than 0, it is known as time delay. Like if we have a signal of this sort, this is x1 0 1 2 3, and then if we delay it by 2 samples, then x of n minus 2 would be starting from 2, right? So 0 and 1 would be zeros, and then starting from 2 2 3 4 5. So this is a time delay, and then if you 2x n plus 2, it will move towards the left side. So this is a time shifting, time delay, and time advance that we are talking about here. And then next thing would be scaling. So the scaling is a bit tricky here. So let's say you have a signal x of n, right? Again, let's just take another example where we have a signal, sorry, right? We have a signal like this, and then we pass this to a signal t, and then what we have, y of n is x of 2t, for suppose. So how do you know, how do you represent this y of n? So if you write it for every n, so y of 0 is x of 0, y of 1 is x of 1, y of 2 is x of 4. So 0, 1, 2, 3, 4. So now what we have, so y of n would be, y of 0 is x of 0, y of 1 would be, sorry, this is x of 2, yeah, and then x, y of 0, 1, 2, so y of 2 is x of 4. But here is a difference between a continuous time signal and a discrete time signal, right? So in a continuous time signal, you can, so basically the information is lost in a continuous time signal, right? If I talk about scaling, here x equal to 2t takes the even indexed samples, correct? Now so someone has joined the meeting, one second. Yeah, for example, if you have a signal like y of t, it is a continuous time signal. So we have y of t is x of a t plus b, which is a affine transformation on x. Can we get back x? Can we get back x of t? Yes, we can. So by y is equal, if we take y is equal to b minus a, so it will be a into t minus b by a plus b, and then we can get back xt. So it is possible to get back the signal after a linear transformation in the case of a continuous time signal, but in the case of a discrete time signal, the samples are completely lost. I mean, when you take here, I mean so here we are completely discarding these samples here, so we cannot completely, so it is a compression that we are doing here, and we are completely losing the samples. So we cannot, this operation cannot be undone, right? So like y of 1 is equal to x of 1 by 2 in the, like for example, if we have y of n is equal to x of n by 2, for example. So if this is another scaling, in the scale of, in the case of x of 2, maybe you can x of 2t, maybe you can 2n, sorry, maybe you can recover. But here x of n by 2, you are losing out some samples. Your x of y of n is equal to x of 1 by 2 is not defined, basically. It is not equal to 0, it is undefined, right? Yeah, so let's just move to an example which can like show the let me see, I just think what example I can give. Yeah, so let's just take an example like, sorry, one second. Let's say you have an example like, so this is a signal that I have 0. So if this is a signal that I have -1, 0, 1, 2, say 3, 4. Okay, so this is a signal that I have. What is x of n minus 2? N minus 2 would be delay by 2 samples simply. So this will be starting from, so instead of -1 it will be starting from 1. So this is x of n minus 2. Another case would be x of 4 minus n. So what you're doing here is take x of n, time reverse it, and then delay the signal by 4 samples. So x of minus of n minus 4. So this will be x of 4 minus 1. If we take these steps in the signal, how do we see it? So x of n, roughly it's something like this. So x of minus n would be, sorry, so this is x of minus n, and then delayed by 4 samples, right? So it should be something like this. So this is 4 minus 1. Here we have reversal and then shifting. So there are two types. So there are two ways where like x of at plus b, if you have, how do you find x of at plus b from x of t? There are two ways. One is shifting and then scaling, and then another would be scaling and then shifting. Okay, so let's take the first case. So you have x of t and you want to scale it by a. How do you do that? You have x of at, and then now if I want to shift it, so this shifting it is done on the independent variable, so it should be x of a into t minus b by a, in order to get t plus b by a, in order to get at plus b, because this is done only on the independent variable. So what you get here, x of at plus b. So this is scaling and shifting. Second one would be shifting and scaling. How do you do this? So first you do shifted by b, so x of t plus b, and then scale. Again we do it only on the independent variable, so it is at plus b. So this is quite simple. I suppose you don't have to calculate this part. So if you are stuck at a problem and you need to get, if you are given a signal and you want to do a shifted and scaled version, I would suggest you, I mean both ways are correct, but I would suggest first shift it and then scale it, so that it is easier to track the signal. So these is an important example where you should be taken care of, or I mean which should be handled carefully. So whenever you are doing a shifting or a scaling thing, it is only applied on the independent variable. So if you see here, it is at, and then sorry, what happened? Yeah, at, and then you're applying a shifting. So shifting is done only on the independent variable. So like for example, if you want to do, if you shifted by a, shifted by b simply, then what would it be? X of a into t plus b. So what you're left with is x of at plus ab, but you only want a shift of b. So this should be handled carefully, right? So shifting and scaling operations are applied only on the independent variable. And then let's say you have another, yeah, let's say you have another type of scaling. So you have x of n into delta of n minus 2. for example. So what is delta of n minus 2? Delta of n minus 2 would be impulse signal shifted by two samples, right? So 0 1 like this. Now you are multiplying with the signal that you have here, which is this one. So this is x of n, this is delta of n by 2. So what it means is x of n into delta of any n minus n naught is equal to x of n naught into delta of n minus n naught. So this is very important. Now this is not equal to x of n naught. This is equal to x of n naught into delta of n minus n naught, but not equal to x of n naught. What it means is, like, so this is y of n. Y of n is equal to x of n naught into delta of n naught n minus n naught, means that what is left is the sample of the non-zero value of delta. So what we left with is this one. So this is 1. Let's say 2 2 2 2 2 1. What we left with is 2. But if you say y of n is equal to x of n naught, it means that y of n equal to 2 for all n, which is wrong. So I hope this concept is clear here. So always x of n into delta of n minus n naught is equal to x of n naught into delta of n minus n naught, but not equal to x of n naught. Hope this is clear, right? Yeah. And then let's see some other example. Let's take x of n into u of 2 minus n. Can anyone help me out with this? Let's go through the step by step. Is anyone there?
Yeah,
Hello? You're not audible.
audible.
Yeah. Can you speak a bit louder, please? I'm not able to hear you. Okay. Sorry, was anyone saying something? All right. Yeah, so x of n is equal to u of 2 minus 1. Now again we have this is a step signal that we have, which is a reversed and shifted. It's a u of n is so on. So u of minus n would be, and then all these values are zeros. But again, u of minus of n minus 2, which is equal to u of 2 minus n. So n minus 2 means delay. So how do you get this? Finally, delay of 2 samples, meaning that correct, 0 1 2. So this is the signal that you have. But then x of n here is, but overlap region of this signal with this signal is only these 4 components here. So x of n into u of 2 minus n would be, and then rest of them would be zeros. X of n into u of 2 minus n, right? Yeah. Let's try to solve one more problem. Let's say you have a signal x of n, which is 1 minus k equal to minus 3 to infinity delta of n minus 1 minus k. So I want you to plot this signal, right? I want you to find the signal in terms of x of n is equal to u of pn plus q. Find p and q. Can anyone help me out here? Hello? First step. What should be the first step? What do you think this part of the signal is? Anyone there? Yeah, I think someone has raised their hand. You can unmute your mic and talk. That's fine. Hello? Yes, Malish. You were saying something. Alright. I'll go ahead then. So let's just put the values of k here. So k equal to minus 3 means that delta of n minus 1 plus 3. Sorry, okay, let's start from k equal to 3. Simply k equal to 3. So n delta of n minus 1 minus 3, which is delta of n minus 4, plus k equal to 4 means delta of n minus 5 plus delta of n minus 6, so on. So what is this? How do I it is clearly visible. So this part would be 1 at the 4th position, this one would be 1 at the 5th position, this one would be 1 at the 6th position. So if you see, it is a u of n minus 4 simply, right? If you see 4 5 6, what's going on? So 1 minus u of n minus 4. But what is 1 here? 1 means like as x of n equal to 1 means all samples are 1. So this part gets cancelled out, and what you are left with is all the samples from minus. So x of n here is equal to 1 for all n less than 4, correct? And then 0 for everywhere else. So it is like 1 1 1 1 1 until 3, and then from 4 it is 0. So how can you represent this in terms of u of n? As we have done in the earlier example, this is u of n, and then we have it in the negative time. So of course it should be transformed as u of minus n, but u of minus n is from 0 to infinity, but we have from 3 to infinity, which is u of minus n, and then we want to shift it to the right. We want to delay the signal. So what is delay? N minus 3. So but then we are doing shifting on the independent variable here. So u of minus of n minus 3, which is equal to u of 3 minus n. So what we are having is final x of n is u of 3 minus 1. So if you write it in terms of u of pn plus q, p equal to minus 1, q equal to 3. Clear, everyone? So until now, does anyone have any doubts?
Can you repeat whole process once more?
Sorry.
Can you repeat once more?
Repeat the last question.
Yeah.
Yeah. Okay. Sure. So what we have is a signal del sigma k equal to 3 to infinity n minus 1 minus k. So if you put values of k here, what you have is delta of n minus 4 plus delta of n minus 5 plus delta of n minus 6 and so on. Correct? So what is delta of n minus 4 here? It is zeros everywhere except at the 1 at the fourth location, plus so this is n minus 4. No, n minus 5 would be zeros everywhere but 1 at the fifth location, and then n minus 6 would be zeros everywhere and then 1 at the sixth location. So if you add up all these signals, what would it be? It is a summation. The final signal will be 1 at the fourth location, 1 at the fifth location, 1 at the sixth location, but then it is going until infinity. Sorry. It is going until n equal to infinity here. So this will go until infinity, which is x. Let's just represent it as y of n here, right? So y of n is equal to this one. So now what does this represent? It is 1 everywhere from the fourth location. Isn't it simply the shifted version of this signal, which is u of n? Correct? So shifted version by 4 samples. It is 1 from 0, but here we have 1 from 4. So this is u of n minus 4. So what we understood is, from k equal to 3 to infinity, delta of n minus 1 minus k is equal to u of n minus 4. And then final signal that we have is f of 1 is 1 minus u of n minus 4. Until now it is clear?
Yes, sir. It's clear.
Yeah. So 1 minus n minus 4. What is 1? It is 1 everywhere. What is n minus 4? 0, 1, 2, 3, 4, 5, 6, 7. What is n minus 4? The signal that we have. It is 1 from here. If you subtract these two, what do you have? It is 1 from 3, 2, 1. So these are all ones, and then these term cancel. So what you have is minus 3, and then zeros everywhere. Is it clear now?
Yes, sir. It's clear.
Yeah. So now what is the signal? So the signal that we have is ones everywhere until n equal to 3. Sorry. 1, 2, 3. But how do you compare this with the signal with the u of n that you have here? This is 1 everywhere from 0 to infinity. This is 1 everywhere from minus infinity to 3. These are related, right? So here we have infinity towards infinity this side, but here it is going this side. So it seems like a reversal operation that we have here. So if you reverse this, u of minus n, what you have is a signal which is 1 from minus infinity to 0, but we have minus infinity to 3. How do we get this? Delay this signal by 3 samples, right? So if you delay this, we get this signal. So what is the delayed version of u of minus 1 delay by 3? What is it? Is it u of minus n minus 3 or u of minus n plus 3? we apply it to the independent variable only, right? So u of minus of n minus 3, which is u of minus n plus 3. This is the correct one. So this is the final answer. So what question was represented in terms of pn plus q. So p equal to minus 1 and q equal to 3. Is this clear until now? I mean, now is the question
Yes,
clear?
sir. Yes, sir. Clear, sir.
Yeah. Okay. Okay. Let me go through. Question. Okay. So did I cover periodicity here? I didn't cover periodicity, right? Yeah. Okay. 1 second. So yeah. So does anyone have any questions until this point, or any questions that you know of, or any doubts that I need to explain? Any conceptual doubts that you want me to explain? Anyone? Scaling. All right. Okay. So let's just talk about scaling for a bit. So we have discrete time or continuous time. Which one? I mean, okay. Let's just talk about both. Why not? So let's talk about continuous time scaling first. So let's say you have a signal x of t, you pass it to a system, and then you get a signal y of t, which is x of at plus b, right? So okay, let's just say only at. Why not y shifting? It's just scaling. In the continuous time case, okay, let's say you have a signal of this sort. This is x of t. What is x of 2t? So y of 1 would be x of 2, and then y of 2 would be x of 4. So this is basically like skipping some samples and taking the rest of the samples, right? So now, for now, in the continuous time case, we have y of 1.5 also, which is x equal to 3. So every point in y is defined here. X of y of 1.1 is equal to x of 2.2. It is defined everywhere. Since x of t is defined everywhere, y of t is also defined everywhere. And then if you see, it is like a compressed signal, correct? So the values at x of 3 are appearing at y of 1.5 only. So it's like a compressed signal that we have here. Earlier the signal would have been like this. Now it is a compressed signal, x of 80. This is x of t. Now if we move to the, so here, since all the values are defined, again from y of t is equal to x of 2t, you can go back to x of t simply by y of t by 2. If we do y of t by 2, what is it? X of 2 into t by 2, which is x of t. So this can be recovered here in the continuous time case. Oh, sorry, I did not see your message. Sampling of discrete time. Yeah, I'm going to explain that next, Pritham. So in the discrete time case, if we say y of n is equal to x of 2n, for example, and you have a signal like 0 1 2 3 4 5 and then 6 for example. So 6 minus 6 minus 3, this is x of n. And then we, so what is y of 0 is x of 0, y of 1 is x of 1, y of 2 is x of 2, sorry, x of 2, x of 4. So what would y of n be? This one, y of 2 would be x of, so x of 0, x of 2, x of 4, x of 6. Similarly, x of minus 2, x of minus 4, x of minus 6. But here, can you recover this signal? So we have y of n is equal to x of 2n. Can you go back from x of n to x of 2n to x of n? Can you apply y of n by 2? That is the question here. So we have an x of 2n that we have, like y of n by 2. So let's say y of n by 2 is equal to y dash. So y dash of n would be y of n by 2. So y dash of 0 would be y of 0, y dash of 1 would be y of 0.5, y of 2 would be y of 1, y of 3 would be y of 1.5, y of 4 would be y of 2. But these samples that you see here are not defined at all. So how do you write this? So y of n by 2, if you take, so if this is the y of n, what is y dash of n is equal to y of n by 2. So what is y of 0? Y dash of 0 is y of 0, which is this one. What is y dash of 1? Not defined at all. And what is y dash of 2? Which is now again y dash of 1. So here this is 1 2 3. It is 1 to 6 here, it is only 1 to 3 here. Correct? So y dash of 1 is not defined, and then y dash of 2 is y of 1, which is x of 2, or like this sample. So this corresponds here, 1 corresponds to 2, 2 corresponds to 4. But what about the samples y dash of 1 and y dash of 3? These are, strictly speaking, not defined. These are strictly not defined. But if you are storing it in a computer, maybe you can do something like putting it a 0 padding, or like put a value of 0 here. So here in this case, once you have done from x of n to x of 2n, and then by scaling of 2, and if you do a scaling of 1 by 2, this y dash of n is actually not equal to x of n, correct? But in the real case, from y of t, if you scale to y of 2t, and then if you scale by 1 by 2, again you get y of t. This and this are equal, but this and this not equal. So basically in the discrete time signal, whenever you are compressing things, you are losing the information completely. But in the continuous time case, you have the signal. I mean, you are not actually losing the signal. I mean, there might be some cases, but here you are not losing any information in the real time case, but in the continuous time, in the discrete time, you are actually losing the samples. But so once you compress it, or once you like sample it with with an a greater than 1, you're losing out the information. You can't get back the signal. So this is a time scaling in the discrete time signal. Is it clear now? Does anyone want me to elaborate it? Like, I mean, any more doubts? Anyone, any more doubts until this point? Okay, so